Hi, myself, Mrs.N. Padmapriya, Assistant Professor of Statistics, Sri Sharda College for Women, Autonomous Salem 16. Today, I'm going to present this video on the topic Introduction and Types of Matrices. In this video, we can see some basic definition of matrices and what are all the different types of matrices and what is determinant, how to find the inverse of a square matrix, and in what field matrices are applied. That is application of matrices. Next, the basic definition of a matrix is it is nothing but the arrangement of the numbers in m rows and n columns, and the entries will be represented as aij. So it is nothing but an rectangular array with m rows and n columns that contains elements or entries. Aij is called a matrix. A matrix is a rectangular arrangement of numbers, symbols, or expression organized in rows and columns. It is nothing but the fundamental mathematical concept used to represent and manipulate the data in various fields. Matrices are typically denoted, that is, it should be denoted in only the capital letters with the element identified by their rows and column position. For example, Aij represents the element in the ith row and the jth column. The matrices are crucial in linear algebra and are used to solve system of linear equations, represent transformation, and perform various mathematical operations like addition, subtraction, scalar multiplication, and matrix multiplication. They find applications in diverse fields including physics, engineering, computer science, economics, and more, and make them a versatile and powerful tool in mathematical modeling and problem solving. Now we see the example of a matrices. So a matrices, that means a complete matrices will be represented in capital letter, and the element inside the matrices are represented in the small letter with the suffix element, that is row and column. Here this matrices, that is A matrices, has two rows and two columns. So the order of this matrices is nothing but the 2 cross 2. So it will be denoted as A matrices is of order 2 cross 2, and the matrix B, it has 3 rows and 4 columns. So order of this B matrices is nothing but 3 cross 4. Okay, then identify the element A22 and B32. Here the element A22 is the element in the A matrices. That means the second row, the element in the second row and second column. So here the element in the second row and second column is nothing but -1. So the element A22 is nothing but -1. Here the element 32 is the element in the B matrices in the third row and second column. So it is third row and second column, the element is 8. So B32 is nothing but 8. Next, we go for the equality of matrices. So equality of matrices is nothing but we have two matrices A and two matrices B. Sorry, we have two matrices A and B. So in previous example, we can say example, we see that there are two matrices. The first matrices is of order 2 cross 2, and the second matrices is of order 3 cross 3 cross 4. Here first when we say the two matrices are equal, first we have to see the order of the each matrix. The order of the each matrix should be equal. That is, if A matrices is 2 cross 2, the B matrices should also be 2 cross 2. That is, when two or more matrices are equal, the concept of equality of matrices is understood. When matrices have the same number of rows and columns and their elements are also equal, they are said to be equal. For checking the equality equality of matrix, equality of two matrices, the two matrices should be in the same order, and the element in the each row and each column of the two rows should also be equal. If that exists, then we can say that the two matrices are equal. Neither of the previously listed property hold for the matrices to be equal. This suggests that the two matrices are considered unequal if the order of the matrices is not equal, or if at least one pair of the corresponding element is not equal. That is, if A 2 3 of the first we can say that uh, if consider a matrices A with order 2 cross 2 and consider a matrix B with order 2 cross 2, we have to say the two matrices are equal if and only if Aij, that is ith and jth column of A matrices, should be equal to ith and jth column of the ith row and jth column of the matrix. That the both now here we see the example for an equality of a matrices. Here consider, here there are two matrices, that is first matrices is of order 3 rows and 4 columns, that is it's of order 3 cross 4, and second matrices is also a matrix of order 3 rows and 4 columns, that is it's of order 3 cross 4. We can say this two, and there are some variables, that is some elements which are missing, x, y, z. In this matrices there are some elements missing, that is p, q, r. This inequality of matrices, there are two conditions, that is the first thing is the order of the two matrices should be equal, and each and every element of the two matrices should also be equal. If this matrix is considered to be an equal matrices, then this element and this element should be equal, that is the first row and first column of the first matrix should be equal to the first row and second column of the first row and first column of the second matrices, so that the elements of the first matrices should be equal to the elements of the second matrices. Here from this we can find the values of x, y, and z. In this matrices, x element placed in the position of first row and the fourth column. Similarly, in the second matrices, the element positioned in the first row and fourth column is 6. So the value of the x is equal to 6. The value of x is equal to 6. Similarly, the y is positioned in the first matrix is positioned in the area in the place of a second row and the first column. Similarly, the element present in the second row of a first column in the second matrices is 12. So the value of y is equal to 12. Similarly, the y value, z value is z is positioned in the first matrices in second row and second column. So similarly the value in the second matrices in the position second row and second column is 24. So the value of z is equal to 24. Similarly, in the second matrices there are some missing values, that is p, q, and r. P is positioned in the first row and first column. So similarly, the value in the first matrices is 3, and q is third row and first column. The corresponding position in the first matrix is 5, and r is it is positioned in the third row and third column. The corresponding position in the first matrix is 49. So the value of p, q, r is 3, 5, and 49. So if the first condition to be the two matrices to be equal is the order should be equal, the element in the both the matrices should also be equal. That is the definition of equality of matrices. When two matrices A and B have the same order, that is the same number of rows and column, and their corresponding elements are equal, that is Aij is equal to Bij for all I and j, they are said to be equal. The primary definition of a matrix equality is given in the statement above, and if any of the aforementioned characters is false for the matrix A and B, the equality does not hold and the matrix A and B are considered to be unequal in this situation. Next, the topic is transpose of a matrix. Transpose is nothing but the interchanging the row and the column of a matrix. That is, basically, the matrix is it is an arrangement of rows and columns. So, if we change the element of rows as a column and the columns as a row, that matrices is considered to be the transpose of a matrix. In other words, if A is an M cross N matrix, that means the A matrix is of order M cross N, then the transpose of A, it is denoted by A, the power of T, or A dash is an it should be an order of N cross M matrix, where the ith row of A becomes the ith column of A transpose. So here is a brief explanation of how to compute the transpose of a matrix. Let A be an M cross N matrix. That is, A matrix is of element M rows and N columns. So this rows is considered to be the column in the transpose matrix, and the second row is considered as a second column, and the M row is considered as the mth column. So if A is of order M cross N, then A transpose is a matrix with the order N cross M, that is the row and columns is interchanged. If that is done, then the matrix is said to be an transpose of a matrix A. Now we see the definition of symmetric matrices. Symmetric matrices is nothing but a square matrices, that is when that matrices is equal to its transpose matrices. That is, if a matrix A after transposing that row and column gives the same matrices, then that matrices is said to be the symmetric matrices. In other words, after interchanging the row and column of a matrices, the diagonal elements will remain the same in both the matrices A and its transpose. So the element above the diagonal and below the diagonal element, if it remains the same after interchanging, then that matrices is called symmetric matrices. In symmetric matrices, the diagonal element plays a major role. Next, we see the definition of a skew symmetric matrices. A square matrix A is called skew symmetric if it's equal to the negation of its transpose. That is, if a matrices after interchanging the row and column, then the elements above the diagonal and below the diagonal elements gives the negative of that matrices, then that matrices is called as skew symmetric matrices. In other words, for every entry Aij in A, in other words, for every entry Aij in A, it holds that Aij is equal to in other words, for every entry Aij in A, it holds that Aij is equal to minus Aij for all I and j except for the diagonal element, which are necessarily 0. In skew symmetric matrix, the diagonal elements will always be equal to 0, and the element above the diagonal element is element above the diagonal element, after interchanging it becomes the negation. In a skew symmetric matrix, the element above the main diagonal are the negation of the element below the main diagonal. So after interchanging the row and column, the element above the diagonal elements will be the negative of the below the main diagonal element. Okay, so in this skew symmetric matrix, the diagonal elements are necessarily 0. That is, ai is equal to 0. This is the example for symmetric matrix and skew symmetric matrices. In this, this is a skew symmetric matrix. After interchanging the row and column of these matrices, generate the same matrices. If that happens, then that is called the symmetric matrices. Similarly, in skew symmetric matrices, here if this element this negation of a minus this element, that is aij is equal to minus of aji, then that element is called that matrices is called skew symmetric matrices. Here in this skew symmetric matrices, here the diagonal elements is all equal to 0, and above the diagonal elements is negation of the below the diagonal element. So this is an example for skew symmetric matrices. Next, we go for a skew Hermitian matrices. A skew Hermitian matrices is also known as skew Hermitian or anti-Hermitian matrix. Is a complex square matrix whose conjugate transpose equal to the negative of the original matrices. Here, this in his skew Hermitian matrices, it contains the complex numbers. In other words, for skew Hermitian matrix A, it holds that A transpose is equal to minus. That is, A skew Hermitian matrix is denoted as A dash, where A dash denotes the conjugate transpose. Mathematically, if A is the n cross n matrix with complex entries, if it is skew Hermitian matrix, that is A transpose is equal to minus A, where A this one is the conjugate transpose of A obtained by taking the transpose of A and then taking the complex conjugate of each entry. That is, a skew Hermitian matrices is nothing but a matrices with the complex entries after interchanging the row and column and changing the conjugate of that complex number, that matrices is said to be a skew Hermitian matrices. The properties of skew Hermitian matrices, the diagonal element of a skew Hermitian matrix must be purely imaginary. That is, the complex the diagonal element should be the contains only the real only the complex part, that is only the imaginary part, not the real part. The off diagonal element satisfied aij is equal to minus of aij, where aij denotes the complex conjugate of aij. That is, the other entries, that is except the diagonal elements, the other element contains both the complex that means imaginary and the real part, and that should be the complex conjugate of that complex number. Okay, so the skew Hermitian matrix has application in quantum mechanics, particularly in the context of Hermitian operators representing physical observable. They also arise in other areas of mathematics and engineering, including signal processing and control theory. So these are the applications of skew Hermitian matrices. So the skew Hermitian matrices is nothing but the taking the transpose and then taking the conjugate of the complex number. And another thing is the diagonal element of the skew Hermitian matrix is always it's a purely imaginary number, and it does not contain the real part. So these are the main properties of skew Hermitian matrices. This is an example for the skew Hermitian matrices, that in square matrices which comprises of complex numbers or real number is said to be skew Hermitian. Then it should be the complex conjugate of the A matrices. Okay, then we see the what is unitary matrices. A unitary matrices is a square matrices of complex number whose inverse is equal to the conjugate transpose. That is, it is a matrix with the complex numbers whose inverse is equal to the conjugate transpose. It's nothing but the taking transpose and then the complex numbers are transferred to the conjugator, then it is said to be an in unitary matrices. Alternative, the product of the unitary matrix and the conjugate transpose of an unitary matrix is equal to the identity matrix. That is, product of any unitary matrix and the conjugate transpose of the unitary matrix is equal to the identity matrix. That is, if U is a unitary matrix and UH is the complex transpose, then U U U inverse, sorry, U U and multiplying U and UH, you will get the identity matrix. That is nothing but UH, that means conjugate transpose of unitary matrix is always equal to the inverse of the unitary matrices. Okay, that is UH into U is equal to U into UH gives the identity matrix, where I is the identity matrix whose order is same as the U. So this is an unitary matrix. Let n be the square. This is an example for the unitary matrices. That is, n is equal to 1 by 2, 1 plus I, 1 minus I, 1 minus I, 1 plus I. On taking the complex conjugate gives the same. So this is an unitary matrices. That is, n into n transpose is equal to n transpose n is equal to identity matrices. Next, we see the definition of an orthogonal matrices. If a product of the orthogonal matrix is nothing but the product of a matrix and its transpose yields the identical matrices, then the matrix is considered to be orthogonal. Let us consider if A is an any matrices, then its transpose A transpose. If product of A and A transpose and A transpose and A yield is equal to gives the identity matrices, then that particular matrix A is said to be an orthogonal matrices. Next, we see what is determinant. The determinant of a matrix, determinant value can be, it is a value which is computed from a matrices. Determinant value will be considered only for the square matrices. Okay, so square matrix is used to calculate the determinant, which is a scalar value or a number. A square matrix could have a dimension 2 cross 3, so should have the dimension 2 cross 2, 3 cross 3 or 4 cross 4 or any other form where the number of row and column should be equal. That is, it should be in a square matrices. Okay, so a matrix, this is a matrix A. So by calculating the value of a determinant for this A matrices, we have to consider it should be determined. It should be determined as a determinant of A or modulus of A, and this matrices should be represented as in the modulus A, B and C. So here the determinant value is calculated by multiplying this diagonal element A into D minus of B and C. So this value can be calculated for the simple 2 cross 2 matrices. Next, how to find the inverse of a matrices. The inverse of a matrix is another matrix that when multiplied by the given matrices yields the multiplicative identity. For matrix A, its inverse is denoted as A inverse, and A inverse is equal to, so multiplying any matrices with its inverse yields the identity matrices, where I is denoted as identity matrices. Consider if A is any matrices with the element A, B, C, D, then its inverse can be defined as 1 by the determinant value of this matrices, that is AD minus BC into cofactor of this matrices. So this is the inverse of the matrix A. Okay. Next, we see the application of matrices. So, this matrices is applied in major field. First thing is linear algebra. That is, matrices are fundamental to linear algebra, serving as a tool to solve system of linear equation, to study the vector space and analyze the linear transformation. Then, it is used in computer graphics and image processing. Matrices are extensively used in computer graphics for tasks like transformation, 3D rendering and image processing operations such as filtering and convolution. Next, it is used in quantum mechanics. In quantum mechanics, matrices, often called as operator, represent physical observables like position, momentum, and spin. They are used to describe the state of quantum system and to calculate its evaluation over time. Then it is used in the field of finance and economics. That is, matrices are used in portfolio optimization, risk management, input-output analysis, and economic modeling. They help to analyze relationship between different economic variable and forecast economic trends. Then it is used in machine learning and artificial intelligence. That is, matrices are central to many machine learning algorithms, especially those involving multivariate data. Techniques like neural networks, support vector machine, and clustering algorithm heavily rely on matrix operation for training and inference. Next, it is used in the field of network analysis. Matrices are used to represent graphs and networks in fields like social network analysis, transportation networks, and electrical power grids. And various matrix-based algorithms are employed to analyze network properties and dynamics. So this matrix is a wide area and it's used in multiple domains. Okay. So now in this video, I just cover the basic types of matrices and its application. Hope I understand. Hope this video will be useful for you for understanding the basic definitions of types of matrices and how to calculate the determinant and the inverse of a matrices. And finally, there are the quiz for this topic is given in the description box, and finally make use of it. Okay. These are the references for the this e-content video, and these are the quiz link and the text material for this topic.